What can we do? Well, let's talk about an algorithm called merge sort. This is a pretty cool sorting algorithm. Here's what you do. You split the data in half, you sort the halves, and then you put them back together. That seems too simple, doesn't it? It doesn't seem like that should work. But it does. We'll talk about it. We'll figure it out. A lot of times you implement this recursively. Where is recursion in this description that I've written here? How is this problem self-similar? Yeah?
You split it in half, and then you send the half of the data back through, and it'll split in half again, split in half again, until it's a very easy chunk to work with.
Right. I mean, he said, well, each time that we split it in half, and then we're sending each of those halves to be sorted, and we're sorting right now. Self-similar means I see a smaller occurrence of my same problem in my problem, right? So sorting 20 things involves sorting 10 things and sorting 10 things. So the recurrence is that I see a half as large recurrence of the same problem on the left and right side of my vector here. OK, it's often implemented recursively. I'm going to show you a diagram of the algorithm running so we can understand what the heck is going on, and then we'll try to write it. The runtime for this I'll talk about in a minute, but it's faster than the ones we've seen so far. Here's the idea. I made a really small array just so I could draw the whole diagram of it running. 8 elements. So what you do is you split them in half. Split them in half. Now you are going to sort each of the two halves. What does it mean to sort each of the two halves? Well, sorting this, what's the first thing you would do to this? Split it in half again, right? Split it in half, OK. It doesn't really feel like we're sorting anything, does it? Well, OK, bear with me. So OK, now we have to sort this and we have to sort this. How do I sort this? I split it in half, right? Now I have to sort this and I have to sort this. That sounds really hard. Well, if it's just one element, there's probably nothing to do, right? A single element vector is sorted. So I don't have to do anything for these. Now that these are sorted sort of trivially, I must merge them together into a whole that is sorted. So I have to take these and glue them back together in such a way that the result will now be sorted. So somehow, I glue those together and it looks like that. I guess I compare them and the smaller one goes first. There's some kind of comparison here to pick which one goes first, right? I'm going to do the same thing over here. I pull these apart. They're trivially sorted because they have size 1. I put them back together in a sorted order. Now, remember, all of this is to sort that thing with the 4 elements right there, right? That's what all of this is for. So I'm supposed to take this, which is sorted, and this, which is sorted, and put them together into a whole that is sorted, right? How do I do this? Well, I think it's kind of like merging 2 individuals that are sorted. You sort of look at these and go, OK, which of the 4 goes first and which of the 4 goes second? And you sort of put them out in the sorted order. So when you put those back together, it looks more like that. I'm waving my hands a little about the merging. We'll talk about the merging in detail in a second. But you sort of look at them and figure out which one goes first, which one goes second. So now I've got this. Remember that one over there? I got to do all the same stuff to it. Split it in 2, split those in 2, split those in 2, merge them back together. Do all this, right? Put those back together. Now I've got this. Of course, the point of all that was to have the 2 halves become sorted. Now I merge the 2 sorted halves into a whole, and my thing is sorted. So I think the splitting is pretty easy to understand. The part that might be hard to understand is just, well, the merging together, exactly how do you do that? And is there a clever, quick way of doing that, right? So here's kind of what you do. You think of it as like I've got these 2 halves, and I know that the halves are sorted. And I just want to make a whole that is sorted that contains all the same contents of both. So what I'll do is I'll start at the front of them both, and I'll compare the front elements of them both. Whichever of those 2 front elements is smaller, I'll take that one first and put it in the result. And if I took the one from the left, I sort of slide my current position on the left forward by 1. If I took the one from the right, I sort of slide my position on the right forward by 1. So I'm coloring in blue. I have int I1 and int I2, like my indexes into those 2 arrays. Whichever one's smaller, whichever one I pick, I move that int forward, that counter int forward, right? And eventually, when I'm done with both of the indexes, I've got a sorted, merged array there. Does that make sense? How long does it take to do that, by the way? Like, if these things each store half of the input, so there's n over 2 and n over 2, there's n total elements between the 2 arrays. How many like compare and put something over there steps do I have to perform here? If this is n as a total, how many compare and put over steps are there? Yeah?
N, isn't it?
It's just n, right. So let's remember that. Merging arrays together is big O of n. So the overall algorithm, like split the entire array in half, put the whole array back together, the part of it that's putting the whole array back together, that one step right there is big O of n. There's a whole bunch of other things happening in the recursion, but that one step right there is big O of n. Let's just think about that. OK. So I want to write this with you guys. Let's go to Qt Creator, and we'll go down. We've got a merge sort method, right? And here, instead of insertion sort, I'll say merge sort. I wonder if I cleared this out. I might still have the code in there. Let me delete it if I did. Yep. Bam. OK. There. So merge sort. I want this to be recursive. So when we do recursion, we do base cases, right? What is an easy vector to sort? Yeah, one element. We kind of talked about that back here, right? So I'd say if v.size is 1, of course, there is an easier vector than that, right? How about if it's less than or equal to 1? If it's nothing, I can sort nothing as also by doing nothing. OK, so I think what I'll say is if the v size is less than or equal to 1, I'll return. Like return just means exit out, don't do anything. Like I could just say if it's not 1, then put the rest of the code. I just don't want to have all the code inside more braces. So OK, otherwise, recursive case. And remember what we said. Like we said split the array in half, split the vector in half. And then we said sort the halves. And then I said merge the halves, right? OK, how do you split a vector in half? Well, there's lots of ways you could do it. I mean, you could make 2 new vectors, and you could do loops for the first half and copy over. You could do a loop for the second half and copy that over. There's a cute little method in the vector class called v.sublist that takes a start index and a length, optional length, and gives you from that index forward by that many. So it basically does this. So I could just say, how about I want the left half and I want the right half to be separate vectors. I'll pull those apart. So vector of ints left is v.sublist from 0 to what? It's the first half, right? So it's the size over 2, right? Size over 2. And then the right side is also a sublist from v that starts at the place the last one ended, size over 2. And then if you don't pass the ending index, it'll just grab from there to the end. I want from there to the end. So I'll just leave that blank. Basically from there to length minus 1 or whatever, right? OK. Those are the 2 halves. So I did this part. I just called the library to do that part. Now sort the halves. Sort the halves. Well, I have written a lot of sorting algorithms today. I guess if I want to sort the halves, I could say like BOGO sort the left half, and I could BOGO sort the right half. I could do that. I don't think that'll be a very good. So I could use selection sort on the left half. I could use insertion sort on the. I guess I could use any sorting algorithm of my choice, right? Which sorting algorithm would you use to sort the halves? Merge sort. You guys are crazy. I'm not even done writing merge sort yet. That's a stupid idea. You're all stupid. I love it. That's a great idea. It's recursion, right? Like if this works, then my recursion will sort the 2 halves for me. Hopefully, I'll write the code correctly so that it'll really do that. And I hope you understand, like if I were calling selection sort here or insertion sort here, you're not going to see the big old speed up that I'm hoping to see here. You're just going to split it in half and call selection sort twice and then put them back together. It's basically going to just use selection sort. It's not going to be any faster. I want to do this all the way down, split in half, split in half. In order to achieve that, I have to call myself. I have to use recursion, right? OK, so merge the halves back together. This is probably the hardest part of the code to write, but I think we can do it. So remember what the slide is showing. Let's make 2 indexes that have these starting points of the vectors. And repeatedly, we will compare the fronts, what they're pointing at, and pick the smaller one and put it into the result. OK? We can do it. So let's make int I1 equals 0 and int I2 equals 0. And that's the index into the left array that we're going to pull from. And this is the index into the right array that we're going to pull from, right? And I think what we need to do is we need to figure out what should go into the result at each index from 0 through size by pulling one from left or from right. So how about for each element that goes from 0 to v.size, we're basically trying to figure out like v bracket I should equal what? It should either equal like left I1 or it should equal right I2. Not both, but one of those two. We should pick one of those two, right? If we pick the left one, there's another thing we should do after picking that. Do you know what that is? This should do I1 plus plus. Move that index forward. If we pick the right one, we should do I2 plus plus, right? The only issue is I need some if-else to decide whether to do this one or the other one, right? So if you're not careful, you end up with like 10 different, well, if there's one over here, and then if this is there, you end up with a lot of cases. I think that most people can see you want to pick the smaller one, right? So you probably want to write something like if left I1 is less than right I2. You might say, should it be less than or equal? But I would say if they're tight, it doesn't matter which one of the two you take. So it's something like this. People end up writing something like that, right? But that's not quite perfect. If we run it with this, it will actually crash. Do you know why it won't quite work? This is really close, but there's something we're not thinking about. What's the problem? Do you know?
That I can get over to these size over 2 and then we're out of bounds.
Yes. So the problem here is that once you've pulled all of the numbers out of one of these arrays, you have to just pull all the elements out of the other one. And so either I1 can go off the end of left or I2 could go off the end of right. And if that happens, you don't want to try to look at that index in left or right anymore because you'll go out of bounds, right? So I think the conditions under which you want to pull from the left side, let's think about them all. So take from the left if one of the following is true. The thing on the left is smaller. That's what we thought of first. But the other case where you would take from the left is what? There's nothing left. There's nothing remaining on the right. If there isn't anything there on the right, and we've already taken all the things from the right, then by default we will grab from the left. So I think the way of representing all of that without a million ifs is to say something like, well, how do I know if you've taken everything from the right? How would I check for that? If I2 has gotten at least as big as right.size, that means I pulled everything out of the right. Yeah? Or, so if that's the case, I want to take from the left. Or, I haven't taken everything from the left, and the thing from the left is smaller than the thing from the right. So like if I1 is less than left.size, and the left thing is smaller. Does that make sense? Like if the right is out, or the left isn't out, and it's smaller, take from the left. It's a little tricky to get the ifs and the elses right, but I think that's the right way to say it. Otherwise, if none of that stuff is true, then probably I want to grab the one on the right side. Either way, once we're done, we will have put all the toys back into V in the sorted order. And that's it. I think that's it. Once we're done with, I'm assuming this works. We can try it in a second. Assuming that this works, that's it. You might not believe that this works. I mean, this might be one of those classic recursion problems where you're like, OK, I can tell all the different steps what we're sort of doing, but I don't really believe that all of those steps add up to sort anything. I guess the way I would say it is think about the small cases where you break a array of size 2 in half, or a vector of size 2 in half. The two halves are trivially sorted, so there's nothing to do. And then I merge them. I merge them by grabbing the smaller one first and the second smallest one next, right? So can you believe me that two things that were out of order would get put into the right order after this code? If you believe me that two things get put out of order, then think about two sets of two things. You start with 4, you split it into two 2s. The two 2s get sorted. If I do the steps here to pick from the two sorted things and put those back together, then do you believe that a thing of 4 would get sorted? You sort of build up your confidence in the algorithm one level at a time. Let's see if it works. I had this one quarter where I was coding this, and I ran it, and it just kept crashing and crashing and crashing, and I was getting really depressed. Like, I was like, man, C++ is really hard. I forgot this part. If you don't have any base case, you try to chop an empty vector in half, and bad things start happening. It happens to the best of us. So up here in the main, I am running merge sort here. Let's see what it does. Let's see if it sorts. Now, it is sorting correctly. Otherwise, the code would throw an exception. So it is working. And those are the runtimes. Now, you might not remember what we're comparing against. Let's compare it against selection sort. Font sizes aren't quite the same, but look at that. It's way faster. Look at how much faster that is. To do 10,000 elements, it took 7 seconds with selection sort. It takes 95 milliseconds for merge sort to finish the same data. Wow. 100, I can't even wait. How far did we even get? We only got up to 40,000 elements with selection sort. We quit out because it was taking forever. I didn't want to literally wait through the whole lecture. 40,000 took 2 minutes. It took less than half a second for merge sort to do the same data. It's so much faster. It kind of blew my mind when I was first learning Big O and learning all these sorting algorithms, especially because I think we have intuitions about runtime that have to do with like the shape of code. Like you look at this and you're like, it's so cute and little and small. Look at it, it fits in 10 lines or whatever. I like that one. And then you're like, rah, oh my gosh, look at all this stuff. It's like 3 pages of code and it's hard to understand and stuff, you know. And I just thought, man, there's got to be some kind of overhead here or something. And it's just so much faster. It's way faster. And let's talk about Big O wise, what's going on here. Because I think this is one of the more difficult pieces of code that we've seen so far in terms of like, what is the Big O? Now, I think I told you what the Big O was 10 minutes ago or something, so it's not like a secret. But how would you figure that out if you didn't know what it was? Well, for one thing, you could look at this, and you could look at the shape of this graph. Now, if you look at the increase of n by 2, factor of 2, what's happening to the runtime? What does it go up by? It's kind of harder to say. It's like maybe kind of by 2, like from 306 to 659. But it goes up by like maybe a little more than 2. Do you kind of see that? It goes up by like 2 point something, 2.2, 2.4. I don't know what. It's not going up by 3. It's not going up by 4. But it's maybe a little more than going up by 2. That little bit is the log n part. N is the times 2 part, and that times 2.1, 2.2. That extra little bit is n log n. So how is it n log n? I mean, you can look at this and sort of guess that, but how would you actually intuit that or figure that out? Well, if you were going to like write out a mathematical proof for it, you can. I'm not going to show you how. That won't be on the test. Don't worry. You can do these things called recurrence relations, where you express runtimes of recursive algorithms in terms of themselves, and you can solve them to find out their eventual expected values, and you can prove runtimes of recursion functions that way. I'm not doing that today. That's a later class topic. But here's the intuition I have. Here's my picture that I like to draw. Maybe this picture doesn't work for you, but when I split and merge the entire array, that takes about n time to do. We said that before. But that makes subcalls. The subcalls split and merge the half-size ones, right? That's this second row of my drawing here. So this, like first, I make 2 recursive calls, right? This one recursively calls this one and that one, right? So it's going to do O of n work eventually, but it also asks this thing to do n over 2 work, and it asks that one to do n over 2 work. This thing asks this to do n over 4 work, and another one to do n over 4 work, right? So this is what's happening in terms of like, if you think of like stuff to do spatially, like this. So basically, if you want to know how long this takes to finish everything, just take the width times the height of the rectangle here, because it's a full rectangle. Each of these rows is sort of n wide. And how tall is it? How many times are we going to split in half like this? When we get from n down to 1, we're stopping, right? How many times do you have to divide n in 2 to get to 1? The log base 2, that's what a log base 2 is. That's what it means to say that something is the log of something, right? Log base 2n means what do you have to raise 2 to get n? How many times you have to divide by 2 from n to get to 1? That's what a logarithm is. So this thing is n log n in size. If you calculated the area of this, it would be n times log n, n log n. That's the runtime of the algorithm. So anyway, that's not a rigid proof. That's how I think of it. That's how I have an intuition for it. So that's merge sort. If you're curious about sorting, there's another algorithm on the slides called quicksort that's even faster still. Pretty cool stuff. Anyway, that's it. I'm done.